Hello everyone. We'll start this session with the title Large Language Models. Are definitely in fashion these days. With the advent of ChatGPT, like about 3 years back, it has taken us by horn. In that sense, it has been used in multiple applications, especially language-related operations, applications, as well as image, sound, and video-related applications. So some of the applications that we can see are search, autocomplete, code assistants. Everywhere, they are proving to be very effective. Now, how these LLMs, large language models, work is what we are going to see in this session. By the way, this session is based on a particular paper on an architecture called as transformer, with which this revolution of LLM started, in my opinion. So the idea of this session, of course, we'll have some introductory slides. Then we will dive little deeper into transformer architecture, and towards end, we'll see some applications. Traditional programming and machine learning, there's a dramatic difference. In traditional programming, we know inputs, we write the logic to convert input to outputs. We write the logic explicitly. In machine learning, it is dramatically opposite, diametrically opposite, especially in what is called as supervised machine learning. We give inputs as well as outputs. Input in the diagram I'm shown as data, inputs and output, and let the computer software figure out the relationship meaning the transformation between input and output. This is the basis of machine learning. This is how the whole AI landscape is placed. AI is actually a very broad term. Whatever we call as human intelligence, if software starts doing it, then it is called as artificial intelligence. Machine learning that we just saw is subset of artificial intelligence. There is of course an AI, artificial intelligence, which is not machine learning, what we used to call as expert systems. These were hand-coded, rule-based, but intelligent systems. Deep learning is part of machine learning. Very superficially, we can think of deep learning as same algorithms, same approaches for classification, regression, whatever, but done using neural networks. If neural networks are used, we call it deep learning. It is very superficial. This is what we will consider for this session. What's the real difference in machine learning? If we are doing classification, we give inputs plus we give what is called as features of that input. So feature engineering is what we do in machine learning typically. And then we give it to some machine learning algorithm and we get output, that is label. Again, this is a very broad, simplistic example. But in deep learning, we don't do feature engineering. We give a raw input and let the feature engineering happen also by neural network apart from this classification related task. So we saw AI, we saw machine learning, we are seeing deep learning now. Large language models that we see these days are actually deep learning based, meaning neural network based. And we'll see more details in that. But this is another important aspect of deep learning is compared to rule-based systems, if you have developed a system using some inputs an expected output, then you have written the logic in the rule-based system. But if you get more data, it is actually more headache. You have to again think how rules can be applied. Do I have to extend? Do I have to edit the rules? So more the data, worse the news, right? It's not good for rule-based system. But that's not the case with machine learning and deep learning, and in that way for large language models also. More the data, better it is because it learns different aspects of the data. So scaling law is actually doing same thing. If you want to have better models, more proficient models, more effective models, dump more data. Of course, dump is the wrong word. Dump, give more curated data. All right. Let's go slowly to what is large language models. So let's see what is a language model. Okay. So one example that I typically give is not exactly language model per se in the strict sense, but this will give an idea of what language model is. Whenever you are typing a SMS, you get some hints in the middle, right, while typing. So this is called predictive text. So how does it give you that word? It gives that word based on whatever past SMSs that are stored in your mobile. So whenever you said, let's go for a, okay, in the past, you might have said coffee for 4 times and movie for 2 times. The likely word that will come now based on the past data. This is coffee, right? That's how. So this is a statistical way of predicting the next word, isn't it? Based on whatever you have typed, based on the data of the past SMSs, you can easily predict what is the likelihood, probability of this word being there based from all the words that I have. So this is what is called as language model. Language model is nothing but predicting next word. Now, the LLMs are nothing but large language models. They are large in two aspects. Large in the terms of data that they have been trained on, and they are large because of the network, neural network that they are based on. So they are language models only. They predict the next word. But what happens when the next word goes back, joins the initial input? Now that forms a new input, again predict the next word. This is how you can see word by word it starts writing sentences, paragraphs, and the whole thing. Right? This is how it works. So these are generative. Large language models are generative because we are generating the next word. By the way, there's a word called token here. Slight meaning difference compared to word. Words and tokens are actually different, but for this slide, the next token is the word only. I'll give the difference between token and a word. All right. Another distinction that we have to know is that generative meaning you generate the output one by one or at a go. Discriminative is where you predict something. You don't generate per se. You predict from the known labels, known categories, and other things, right? This is discriminative. Typically, most of the machine learning models, the classification models, or regression models are discriminative. They just give the value or label, but generative, it generates the output. Generates the output. By the way, there are machine learning models also which are generative in nature, and there are neural network models as well. All right. I'm just giving background, although some of the concepts may look little off the line, but with all these concepts, then we will start the transformer architecture and then we'll try to connect the dots. So this is what we saw in the word embedding session. There are statistical approaches. What is word embedding? Word embedding is a way to represent text in numeric form. Numeric form meaning vector form. Vector is nothing but list of numbers. So there are multiple approaches. Typically, there are two types of approaches. Statistical approaches or frequency-based approaches, count-based approaches. We saw bag of words, one-hot encoding, TF-IDF. These are statistical, count-based, frequency-based approaches. And the newer ones are typically neural network-based approaches. Word-to-vec, transfer models that we are going to see, BERT and other things, all these are so-called modern, but neural network-based approaches. All right, just summary, just have a look at it. I won't go through it. Another thing that we keep on hearing that this LLM uh, has 175 billion parameters. ChatGPT is actually a front end. The model behind it is GPT or used to be at the start GPT 3.5 instruct model, and it had 175 billion parameters. What is this parameter thing? If you had seen machine learning, we discussed what is called as regression. Regression is nothing but fitting a line basically between the data points. And typically equation of line is y is equal to mx plus u or ax plus b, right? This is the, there are, what are unknown coefficients here, a and b. These are actually parameters. Similarly, just see y is equal to mx plus c has two parameters, m and c or a and b. LLMs are built on networks where there are 175 billion weights or parameters or variables which are trained based on the data. This is huge number. That's why they are very, very effective. Here we saw two parameters and we are in GPT 3.53, 175 billion parameters. Such huge network it is. That's why it is called as large language model. And in all the training, all these weights get updated. We'll see the transformer architecture. Wherever there are weights, they are adjusted during forward, during back propagation. So multiplication happens in forward pass, and in the back propagation, all the weights are adjusted so that the error is minimum. We'll see that process. All right. Another concept that I wish to touch upon, as I said, LLMs or the input data is not fed as words as is, but as tokens. Let's see the difference. Token is actually sub-word, part of a word. So typical English word is say playing. It is broken into two sub-words, say plain ing. And the way we break these words, there are multiple algorithms. There's a BP byte pair encoding algorithm, word piece algorithm. Why it is done? Because as you can see, vocabulary wise, once the words are broken into token, vocabulary wise, the size reduces because in playing, play and ing, in say going, go and ing, that ing is common, right? So it is stored only once. That's why all the INGs token is one. Able token is one. Un token is one. So that's why vocabulary is reduced. Because less the vocabulary, less the storage, and less the compute, so on and so forth. So this is how we don't use words directly, but break them into tokens. By the way, this is very similar to what we discussed in NLP called as stemming or lemmatization. More of a lemmatization, meaning breaking, but the words still have some kind of meaning. So these are some of the concepts that we are saying which will be useful in the core of the session today, that is transformer architecture, the architecture that is behind large language models. All right. Another thing, we saw one example that large language model is nothing but predicting the next word, isn't it? And we saw SMS example. it had two options, going to a coffee or going to a movie. This is a very simplistic example. For a large data set, there could be multiple options, isn't it? So, I've given an example here. The best thing about AI is its ability to. Now we are trying to predict the next word, and there could be many, many options available for us. Shown a couple of them here. Say ability to learn, ability to predict. They come up with us based on the probability. In case of coffee and movie, it was 4 times and 2 times. So probability can be easily calculated. Similarly, nothing but what is called as ranked probability distribution. To put it in plain English, I have so many words. What are the top possibilities? Right? Top possibilities after its ability to, right? Here, there are multiple approaches, even to select from the top base. There are 3 or 4 ways for sure. One we have shown here, this is called a sampling strategy, meaning greedy, meaning pick the best. Very simple strategy. So whichever has most probability. Here we are saying learn, right? Actually, all these are reasonably okay options, but still, learn has the best probability because in the training data, learn came more times for such phrase than predict. I hope you're getting. I'm giving a frequency like or probability like explanation, but neural network spits this way probability. Temperature again is another thing. Instead of just sticking to only top one, if the temperature is little temperature meaning relaxation, creativity, some randomness, then it is okay to give predict also as long as it has certain probability, right? More than 3 or something. So there are multiple strategies to give. The next one. Why it is done so? Why not give the top probability only? If top probability is given, the the output for this sentence will always be learned. Sometimes you need that. Deterministicness is needed where greedy is used. Temperature is zero, meaning no chaos, no randomness, no creativity. Give me a definitive answer. But if temperature is little more, meaning creativity is more, sometimes you want different sentences, right? Not the same poem all the time. So some variety you want. So there we set the temperature to zero point 0.8, zero point 0.9, something of that sort. By default, I think ChatGPT has 0.7. All right. So these are some of the concepts which will make us ready to learn the transformer architecture or LLM. Here are some of the strategies. Although these topics would look little premature while we are discussing it now, they'll come handy once we understand the transformer architecture, and then you will be able to connect the dots. Greedy, as I said, best one. Top case sampling, sample from most probable, if K is 50, sample from anybody in the 50. Top P is nothing but you calculate the cumulative probability, cumulative meaning added. More than say zero point 0.9, everybody is okay. Anybody from that is okay. So there are multiple strategies for predicting which word is the next word from the eligible words. All right. So we've covered basic ML, AI, ML, DL, and some concepts. Now we are slowly coming towards transformers. We are not there yet. I still wish to cover what were things before transformer which had some issues and because of which transformer came into existence and how it solved those issues. This is what I'm trying to get at. So we'll discuss 3 things now in this session, part of the session. Embeddings, we sort of covered word vectors, and we'll cover what is called as sequence to sequence, encoder decoder networks. This is the foundation of the transformer architecture. And there's a special thing called attention. This is also what we'll discuss in this sub-session now and also cover in more details in the transformer session. So these 3 concepts are important before we move to transformer architecture. As you can see, transformer architecture needs a lot of preparation before understanding that architecture itself. All right, we saw that by various approaches like statistical approaches, neural network based approaches, we can have a numeric representation of a word. Numeric representation meaning a vector, list of numbers. And last time we saw it is just not semantic, meaning a word like apple, a vector for an apple and vector for an orange. Their cosine similarities they're very close in that nth dimensional space. This is what we saw in the word embedding section. Or the distance between them is very small. They are very similar geometrically also and meaning semantically also. Another property we saw of word embeddings is that they obey vector algebra. We saw that difference between king and a queen. That difference, if you put on man's point, at the end of that vector, difference vector, you get woman, right? That's what we saw. So these are the properties which are essential for LLMs, large language models. On these concepts that I'll cover now, three concepts, the LLM is based on. All right. This is a fundamental approach which was very popular before transformers. By the way, there is a paper um, on RNN is nothing but recurrent neural network. These are sequence-based neural networks. Other neural networks that you may be familiar with are ANN, CNN. CNN is convolutional neural networks, typically used for images. Of course, used for languages also. 1D convolution is used for typically language. 2D convolution is typically used for images. And another next one is called as sequence to sequence. There RNNs are used. RNNs and LSTMs, long short term memory networks. I'll explain this in more details because this is the foundation for the transformer architecture. Okay. Assume that you are, again, this is a next sentence prediction, or another case is machine translation. Let's think of machine translation problem. How do we train a neural network to convert English to German? Okay, this is the problem we are working on. So we have lots of pairs, examples of English sentences and their corresponding German sentences. Now we wish to train the model, and the model for such problems or applications is encoder-decoder network, because there is an input and there is an output. Encoder will encode the English sentence, put it in some representation, what is called as latent space or hidden vector, and then that hidden vector will start outputting the German words word by word. While training, you give both. It understands the corresponding relationship. For this word, this could be the one, this could be the one. It understands that thing because of backpropagation, neural network backpropagation. And then once it is fully trained, for any unseen English sentence, it can spit out the German sentence. For such problems, RNNs were used, recurrent neural networks were used. And you can see this, the green part, this is the encoder, and the blue part is decoder. By the way, we are seeing it, one word is going in H0 box. By the way, these boxes are nothing but RNN cells. RNN cells are nothing but for an input vector, which is say one hot encoding vector for hello or Kirill or whatever. They do some matrix computation, matrix multiplication, and give out the output. Right? That's what they do. In LSTM, it is little more elaborate. They have some forget gates and other keep gates also. Let's not worry about that. RNNs have some matrix calculation, that matrix of weights, which gets learned and it decides what to pass. one fundamental mistake that people do is that this seems that there are four RNN cells or n RNN cells parallelly. That's not the case. There is only one RNN cell here, and these are shown as a timestamp thing, meaning first word goes as hello, same RNN cell next timestamp, period goes. Some computation happens. Again, the next word goes. Again, the next word goes. Cell is just one. Just for understanding purpose, it is laid out in the time scale. Cell is only one. That's why it is called as recurrent. It is occurring again and again, same cell. So only same weight matrix is updated. So that's the encoder part, and decoder gives out the words one by one. This is RNN. And I think there is a very famous paper in our times, so-called our times. It used to be with unreasonable effectiveness of RNN. If at all you're interested, search and then try to read that. Now it looks very old, like old in Hindi movies. It looks little dated, but this was very effective that those days. So this is RNN. Now there are two main problems with RNNs, and you can easily see them. Typically what happens, one word goes, calculation happens, second word goes in the same cell. By the end of the sentence, it has computed logic of all the words. And whatever remains, that vector, say this one, which before going to decoder part, does it have really good understanding of all the things that it is learned? It is such a compressed representation, only word vector like representation. Now this is representing the whole sentence. Now what happens? Like even humans, if we start hearing few things, we tend to forget the earlier ones. You only remember the recent ones. This is what happens here also. Another thing that happens here is what is called as vanishing gradient problems. While doing back propagation, the weight matrices have smaller values, weights typically. And after a couple of weight matrix multiplication, if you multiply a fraction with a fraction, that fraction becomes smaller and smaller and smaller. After some back propagation stages, everything becomes zero. So basically it forgets. So this is the main problem with RNS, that it has vanishing gradient. Gradient goes to zero, and so no learning happens later. Another problem is it is sequential. Unless first word is processed, next word cannot go in. Unless the next word is processed, the next word cannot go in. So it is sequential, so very slow, and we cannot leverage the current architectures like parallel processing, multiple GPUs, we cannot leverage. So two main problems with RNNs, uh, which we will try to see if the transformer architecture solves them. That's the idea of the whole session today. So one thing that we can do some parallelization, what is called as attention. So there was an attempt to attention even in RNN based things also, but we will see them in transformer case push. All right. Okay. Another important thing that we are supposed to solve. Okay. Let's take a given example here. Let's say if you want to calculate, um, I'm taking one example, word embedding, meaning word vector for word apple. Okay. Now, apple's vector can be seen in the context of fruits and also in the context of companies. Apple company, which makes whatever iPad and other things, right? So, what should be that representation? While doing the training, there could be fruit related sentence in the training. There could be companies related statements in the training. So the final word embedding for Apple may come out to be some mishmash, some mixing things also. So not useful per se, right? Because we really want to understand from the vector, what's the thing? What is it representing? So we cannot have a single vector representation for word apple, but the representation should depend on the context in which it has been used. So if the sentence was, I love apple juice, there the apple is fruit-like, or Apple posted record revenue. In that case, it is company-like, right? Because this famous thing, a man is known by company it keeps. So similarly, there is a famous saying, you shall know a word by the company it keeps. So this issue that single word meaning should have different representation because it means different things in different contexts. This is another thing that will get addressed, resolved in transformer architecture, and this is done by attention, self-attention mechanism, which we are going to see. So far we have covered a lot of sporadic concepts, and slowly now we will go to transformer. Okay, there you go. The architecture of transformer. I will wait here, let you read. Of course, we'll explain these blocks one by one. And the papers that propose this architecture, probably almost everybody knows who is working in AI these days. Attention is all you need by Vaswani and other players. By the way, there is one person from Pune also, which is a co-author. I will let you find out who that person is. So, by the way, this is the diagram. If you want to take a screenshot and keep it ready, besides you, that would be also wonderful because I'm going to explain this diagram for the rest of the session and of course before the applications and other things. So let me just go over it one by one. This high level, the left-hand part is called an encoder, similar to sequence. Encoder first, this is the encoder part. Input goes in, something happens, which we'll see. And the encoder gives the hidden representation in a vector form to decoder. And this is the decoder part. Decoder also has its own inputs. Say if it is an English sentence here, it is a German sentence here. It also processes text, the hidden context from encoder and processes further. Just remember this. We'll see all these blocks, how inputs are converted, then what is positional encoding, what is multi-head attention, before that what is self-attention, which is part of multi-head attention, what is feed forward, all these blocks we are going to see. By the way, these blocks and blocks used in decoder are more or less similar, slight difference, that difference also we will see. But further things, more or less same. Right? This is encoder-decoder architecture proposed by this paper, and this is the foundation of whatever revolution that happened in large language models. ChatGPT, it is the GPT, generative pre-trained transformer. The transformer is this transformer. Of course, it may have enhancements later on. And the NX shown here is number of layers of such blocks. I think this paper has 6 or 7 blocks mentioned, but say GPT has 96 blocks on the encoder side or whatever. So typically these number of blocks differ. Another thing that I wish to mention at this stage is during training, what happens? Say if you have English sentence and output is German sentence. English sentence is vectorized, matrix multiplication happens, then in the output also matrix multiplication happens, and another matrix multiplication element goes here. Now we have input as well as output. Here, after all these calculations, some vector representation comes. It is matched, it is compared to the known one, known German sentence vector representation. The difference is calculated, the loss, and the loss is back propagated here, here as well as here to adjust all the weights used here. Getting what I said? This you have to understand. This is the crux of the of understanding transformer architecture. You had input sentence, some processing happened, and it gave predicted output. But predicted output is different from the actual output, at least initially. That difference is backpropagated in both decoder side and encoder side, and all the weights are adjusted. This happens for multiple pairs of English and German sentences, multiple times, till the time the weights are settled. Once the weights are settled, the transformer is ready to be used. How do we know? Given any known English sentence, it starts outputting. Weights are adjusted so that it starts outputting the needed German sentence. This is the main idea of transformer architecture. So this is encoder decoder transformer architecture. Two more things you might have heard: encoder only transformer architecture and decoder only transformer architecture. These are nothing but this portion is only used and trained. Only encoder portion. You will see that. And one of the famous example for encoder only architecture is BERT. Another thing is only decoder is used, trained and used. This is nothing but GPT. GPTs are decoder based generative transformer, generative retrained transformer. These are decoder only. And there are encoder decoders also, which are little less famous. T5, T as in train. T5 is a relatively known encoder decoder based architecture. All right. We'll see now these blocks which make the transformer architecture, and then we'll understand what's going on. So what happens? Input sentence comes, we do tokenization. Tokenization meaning sub-word splitting. Each token gets an ID. So if there are 10,000 words in the whole vocabulary, 10,000 IDs are given. So further now, there are no strings, there are only IDs. And of course, word vectors associated with the IDs. ID1 this word vector, ID2 this word vector, something of that sort. So tokenization and token embedding. By the way, token embeddings can be generated within the transformer architecture also by some neural network architecture, or you can feed them as ready word to vects. But as here mentioned here, they are learned during pre-training only. All right. There are two main concepts that we are going to see in this transformer architecture. This is the one, and there's another one called self-attention. These are, in my opinion, one of the hallmarks of intelligence, how people have invented things. Now, first one is positional embedding. We'll try to understand very well. Another concept that we are going to understand very well is self-attention. If you understand both of them, rest of the things is just basically details, right? We saw that RNN had a problem that we processed things sequentially. And in transformer architecture, one of the main differences is that we process all the words parallelly. Okay, all the words come together, the whole context, meaning whole input sentence comes parallelly. Each word gets processed parallelly, separately, individually. That's how we can leverage the GPUs, parallel processing GPUs. That's why there is a big race for GPUs because they can do parallel computation. And it saves time and other things. That's the advantage of doing parallel processing. So transformer is better than RNNs because it does things parallelly, not sequentially. But as we move to parallelized architecture, there's a big drawback which RNN did not have because language is sequential. Cat sat on a mat is different than mat sat on a cat, right? If you are doing things parallelly, cat will go here, mat will go here. There is no relationship. So we need information about its position in the sentence, right? Unless we put position information in this along with the word. Say cat is the first word, sat is the second word, mat, and then process. And then once we compose them at the end of encoder, we can carry that position information. So although parallelization gave that advantage of speed, but it lost the order. How do we get that order back? So we have to add position information in each word, input word embedding, right? How do we add them? Simplest answer could be for the first word add 1, second word add 2. But this is not going to work. You can easily see if there are 20,000 words in the sentence. I'm just taking words example. But then the last thing will get added by 20,000. By the way, these are neural networks. These are input values sensitive, right? Because weights are getting multiplied. So the last word is not the most important word, and the first word is not the least important word, right? That's not the case. So we have to have these additions. The position information that we are going to add has to be some reasonable values, bounded. This is what is called as bounded. If they are bounded in say 0 to 1 or -1 to 1, sort of okay. They're not adding too much weight to the input word embedding. So first requirement of positional embedding is that they have to be bounded. Another important thing we saw in the apples case, based on the surrounding words, the apple, if it is fruit, it has to behave, it has to have some different values. If it is a company apple, it has to have a different value. That idea has to be also put in place. So first requirement, it has to be bounded. Another requirement is it has to be unique. Okay. So some genius who is one of the co-authors has come up with a very simplistic solution to address both. And you can see the genius here, how positions are encoded. Simple problem. They use what is called as a sine curve. If you all remember the sine curve is like this. The main property of sine curve, it is bounded. Bounded meaning it has values between -1 and 1 only. -1, 0, 1. So sine 1 something, sine 2 something, sine 3 something. If the frequency is say of 3, then you start getting minus values. At 6, the full wave is over. Then again you for sine 7, you get the repeated values. So values wise, any index, any position, if you take sine of it, it is always between -1 and 1. That problem is solved. But another problem, just using the sine wave, if you can see, so of frequency 3, frequency is the wrong word, one curve is in 3 and the bottom curve is in 3. So 6 length is a one wave. Okay. After 6, the sine 1 and sine 7 will have same value. If you can see it, because it is repetitive, it is sinusoidal, it is cyclical in nature. So the values will repeat. How to solve that? So sine 1, so uniqueness is gone. The value added for 1 and value added for 7 is same. So another trick was done. So we took sine wave of certain frequency. We also added another parallelly a cos wave, meaning it is phase lag, right? cos is phase lag 90 degrees. Added sine wave. Even combination of these two, meaning this value, also this value will become a vector for that position. So position is an embedding. It is a vector for that word, meaning position. Even this combination of sine plus cos will may have some repetition later. Another thing was done. So sine and cos waves of say length 6. They added another pair, sine and cos. Say with a smaller frequency, meaning more waves within 6. Different shape. Such pairs were added. And with if you just imagine, I'll show you the picture. If you see the vertical slice of a position, then that vector will always be unique for that position. This is how some genius thought of it. Very simplistic solution, but very effective solution of encoding indices, encoding positions in the positional vector. Mathematics is a little crude, but if I can just simply say, this is position for which we are encoding, say 1, 2, 3, 4, this is k. 2i is nothing but which wave are we using? So this is for even waves, and this is for odd waves. These are typically cos ones, right? Um, so as I saw, phase lag of 90 degrees. This example, it will be very clear. This is the sequence. I am a robot. Input token indices are these. These are its positional positional encodings. P00 is nothing but this formula. I P00, P10. For each word, we are getting positional encoding of D length. D length is nothing but the vector, the word embedding vector that we want to do. I'll show you one more slide and then things will be clear. I'm probably sure if you have not done similar things before, this is going to be a little difficult to follow, but at least intuitively, if you can follow, that would be wonderful. All right, this is what it is. For each position, you get some slice of a sine wave, some slice of a cos wave, another sine wave, another cos wave. So vertical slice of each position, it becomes the positional embedding. This is how it is. Now things will be clear. This is a sine wave, so this is of different frequency. This is again of a different frequency. For this slice of a position, different values of different waves are making a vector out of it. That's how position encoding was done. I hope at least some intuition may have come. On. I'm just giving you, and that the formula was used, and this is how it is. Okay. Wait here, you grasp it. Just assume that these words come in, they come in as a vectors, and this positional embedding is added to it. So position, and as you can see, these values are very small. These are values are bounded. So meaning wise, the word vectors don't deviate too much, but the position gets encoded. By the way, this is positional embedding. Nowadays, a different positional embedding has been proposed. I think this is, as I mentioned here, this is called as rotary position embedding, which is now relatively famous than the transformer architecture sine cos wave based encoding, positional encoding. So this is first concept that I wanted to touch upon, and another concept we'll see now, a very important concept, self-attention. Okay. Now we saw that problem. Apple has to have a different meaning. If it is a fruit sentence, it has to have a different value. If it is a company finance or company statement, it has to have a different value. How do we do that? We have sentences coming to us. What do we do so that a word looks at its context? and modifies itself, its word vector. This is the concept we are trying to see. Okay. So the trick that is done here is what is called as attention. I will explain two processes and then we'll see the formulation. So um, this is the sentence that has come, three words, and these are word embeddings with which they have come. What they do, they make three copies of it. Why three? We'll see. There is a theory behind this from information theory. They call it um, KQV, query, key, and value. A word, we are trying to query it in a database. This is Q. Keys, we are trying to see which key matches to it. This is nothing like a word being searched in an indexed database, which has key value pairs. So query comes, it is matched to key and its value is given. So this paradigm has been used. By the way, this is just a paradigm which is easier to understand, and this is the way it is done. So three copies, you can see same copies. What is done this? These copies are transposed /t, and then multiplied to it, you get a 2D matrix. 2D matrix, all things are normalized by softmax, meaning 0 to 1, -1 to 1 type, 0 to 1 typically, and again multiplied to this x. You can see this. This is how we get the attention scores. I'll show you the next slide, which is clear. Now, if this process is clear, this goes to the next slide. Once it comes, this one, this is the value matrix, and you get once we multiply them to the original word vectors, this matrix vector, you get this. This is nothing but the attention vector. Okay, this is how you get the attention vector. This has encoded for a word other words information, because every word's information has been used in multiplication. But the bad part of this is there is no tunability to it. Word vectors came in, you multiplied, but where are weights here? Weights are not there. What can you tune so that the three copies are actually giving the contextual understanding to it? So there comes tunable self-attention. And these things could be little tricky, but still, I'll go over. What we have done, same process. Only thing that we have added AK is nothing but a weight matrix. So original X came while making three copies, we multiplied each of them with weight matrices. Weight matrices are variable to be tuned in backpropagation. Okay. So once we have X that has come while making a copy, we multiplied by weight, we got K. Similarly, second copy, AQ is nothing but a weight matrix. You got this, Q. This thing was multiplied like last time. You got QKT. This thing again, same thing. While doing AV, another weight matrix, and you got the same thing. Now, you got the same attention score. Attention score is nothing but a list of numbers for a word which is giving the weights to its neighbor, which is more important for me. As an apple, if I'm doing, I love apple juice. Apple is more, will be more towards juice, right? It is the distinguishing factor for it. So its weight will be more. So that thing is computed, but now, as there are weights, this importance is not hand coded or hard coded. It gets adjusted by the backpropagation. So the shift of Apple towards this way or that way is getting trained only. I'll give that example now. It may be little not legible, but this is what happens for each word. So this is Q love, Q love, Q love, right? It started with this, then it got multiplied, softmax, and then added to it. So it got score. Again, it has been, I'll wait here till you read this. But same thing, if you can remember, X came in, weight matrix related to Q, got Q. X came in, weight matrix related to K, got K. X matrix, weight matrix related to V, got V. Attention KQV is nothing but we multiplied that thing in the second stage. This is nothing but a normalization step. Normalization divided by the length of the dimension, square root of it, and then multiply. This is nothing but the scores. This is nothing but for a word based on the neighborhood. What are my weights? What are my score of importance? This is what I'm getting. How Apple's contextual embedding for a word, contextual embedding has come. Another important thing that this attention mechanism gives is relationship. Meaning, let's say take an example. Um, Ram ate apple. He ate orange also. Now that he refers to Ram, right? That thing also is calculated in the training. And the for he, the most important score, weighted score for a word would be Ram, and then vice versa. That's the idea. This is how you get the importance of a word with relative to its family, it's related to its neighbor by this. All right. So these were the two main concepts: positional embedding and attention, self-attention. Why self-attention? Because we are attending, we are giving focus only to my own input sentence only. I'm not looking at the output. That thing is called as cross attention. If and that typically happens in decoder. Decoder sentence looks at encoder sentence, input sentence, and then tries to decide which is more relative to relational to it. Here, within sentence itself, I'm trying to see which is more related to me. Right? That's the idea. All right. This is the step. Same thing that I showed. This is nothing but now input embeddings as they are multiplied by these attention scores, they are more contextualized. Let's recap. You started with word embeddings, you added positional embeddings, it became more position aware. Same things when they calculated self-attention. Self-attention was dot producted on top of it, meaning position-wise multiplication. Now they become more contextually aware. The input sentences became richer and richer. Then the final feed forward network happens and the encoder ends. This is the process of encoder. I will repeat once more. I hope you are getting it. This is the diagram typically used for this word. These are the ones which are very, by the way, the darkness of the line gives the attention score thing. Another problem. Okay, by the way, this is the self-attention within this. Another problem that you may see in typically NLP, that the same sentence may have two different meanings. Initially, we saw Apple had two different meanings. One word, two different meanings. One is a company, one is a fruit. Now, there are situations where same sentence has two different meanings. Little rare, but they are there. And one of the examples that I'm taking here is, say this sentence. She saw the man with the telescope. Can you see there are two meanings? She saw the man who is having the telescope. She saw. But she saw the man with the telescope. She's watching through the telescope, the man. Right? Same words, two different meaning. Now, how to solve this problem? Now, this problem is solved in transformer architecture by doing this self-attention thing multiple times. Each self-attention will have three weights, right? Three weight matrices. They are initialized differently. They are learned differently. Similar three weights give another head. By the way, this is called as head, attention head. Another attention head, different three weight matrices. Another attention head, different three weight matrices. While learning, they look at different sentence pattern, sentence understanding. That is how same sentence, different understanding is captured. Doing attention, but multiple times. That is what is called as multi-head attention. This is nothing but concatenation, head 1, head 2, head 3 concatenated. I think then they again collapsed back to the same length vector. Bird has 12 heads, meaning 12 times the attention mechanism is done. Head typically, although this is not very, typically this is doing syntactic arrangement, subject verb kind of thing. Another pattern it learns, head 3 learns another patterns. More the heads, more the pattern it learns. So repeat the is 96 because there are 96 blocks. All right. So these were the two main concepts. We'll just do a recap of what by the so last few things of the same architecture. Once these word embeddings get positionally enriched, contextually enriched, then typically we may have actually add non-linearity. We do normalization also just to put them in bounded way. And sometimes we do what is called a skip connection. Instead of to address the vanishing gradient problem, we skip certain layers and go back to the previous ones. This is called a skip thing. These are typical deep learning based techniques to avoid overfitting. Okay, and layer normalization. Once this is done, then the final feed forward network FFN is used. If you want to do classification, then you can put labels at the end. If you want to do encoder decoder, then the whole thing is passed to the decoder. Okay, that's the idea. Just if you have just encoder, FFN will have some labels or whatever, classification or NER kind of labels. This is the summary slide. Tokenize, embed, add positional embedding, do multiple multi-head self-attentions, normalize the whole thing, feed forward network. Repeat. One block is done, another block like this, another block like this, another block like this. Once everything is done, finally, if you want to do classification, then that label thing and then back propagate the whole thing. That's the idea. We just touched upon encoder set. I'll quickly cover. Decoder is more or less similar. Decoder has its own inputs, does the same thing, but finally has softmax similar to this, and then decoder does the thing, similar things. So I won't repeat that explanation. All right. I hope at least the blocks in the transformer architecture are sort of clear. As I mentioned, there are three ways to use transformer architecture: encoder only, encoder decoder. They're actually part of the same architectures, whatever I explained. Only the training way is different and the usage way is different. We'll quickly see how the training is different and usage is different. Okay. What we saw actually now is encoder decoder, which is used for translation. Okay. So initially one may think this encoder decoder transformer architecture is fully trained by machine translation like thing, and only encoder is used for BERT like things. That's not the case. Or any decoder is used for GPT like this. That's not the case. All three paradigms are trained separately. Encoder only architectures have only encoders. They are trained only encoder way. Decoder based only architectures are only decoders. They are trained decoder way. And encoder decoder is the way that I've mentioned so far. So this is what this thing mentions. So encoder only is nothing but this is trained by what is called as masked language modeling. Okay. Given a sentence, say a word is temporarily masked, masked meaning hidden, and that thing becomes output to be predicted. Getting what I'm saying? So this is how it learns. Why? So no separate labels are needed. No separate supervised training data set is needed. That sentence itself acts as an input, and its word acts as an output, right? As you can see, cat sat on a mat, right? Here the mask one is sat, mask two is mat. So both, so this is what is called as self-supervised, because the same input is converted to input and output. And this is how classification things and other things are done. So by the way, encoders are typically used for classification and other things, and also for vector embeddings, generating vector embeddings. BERT is a very famous example. You have input sentences. Once it is learned, instead of using the final softmax layer, whatever embeddings that you got so far, just one level, one layer before, these embeddings are used as word vectors. That's what is typically BERT is used for. All right. Decoder only. For decoder only, the input is a prompt-like thing. Now we call it as prompt, and it predicts the next word. So what is the input? Input sentence. By the way, given a corpus, you can easily do that. For a word, next word is known. So that becomes output. So this is input, that is output. Now, once that is predicted, that whole thing becomes input, its next word becomes output. So this is called as causal or auto-regressive language modeling, right? This is how it does. So input and output are generated from the same corpus and it is trained. By the way, as there is no encoder here, no encoder and no cross attention. From attention from decoder side to encoder side is not there. And typically most of the LLM that we use as ChatGPT like thing are decoder only because they generate word by word. Given a prompt, they generate. All right. This is how GPT inference happens. This is nothing but decoder based thing. Same thing happens. Say this is a prompt. Sky is translated to French. Sky is. Now this is the input. Tokenize, add positional embeddings, decoder layers, same as attention thing. And then once the thing is calculated, project back to vocabulary, meaning which next word's ID is closest to that vector. That thing is given. So assume that it comes out to be blue, blue. I don't know what is, or blue. Um, so then blue is added to this. The sky is blue, and then the whole thing becomes input again. Then the next word till you get end of sentence. So end of sentence, EOS or end of text. This is a GPT inference. And encoder decoder is nothing but translation input and say towards German. Their attention also is there and cross attention is also there. So T5 and BART, not BERT, BART. These are used for translation, abstractive summation, big paragraph, small paragraph, that kind of thing. Dialogue, all Q&As are done this way. All right. So this is the summary of so same transformer architecture used in three flavors: encoder only, decoder only, encoder decoder. All right. This is what I wanted to cover. Um, Use cases, I think the further slides are relatively simplistic. Use cases, all multiple use cases, LLMs, wherever they are used in these three flavors. And I'll go fast now. Few more things which are very relevant to LLM development. Pre-training is what we saw today. Then, of course, prompt engineering, supervised fine-tuning. Given a model, can we have additional data, either change the original weight or have added another neural network to fine-tune the given data? So this is what is called the LoRa method, which if possible, we can have a session on that LoRa way of doing fine-tuning. Reinforcement learning is another thing, use as SFT plus RLHF is what is typically done in generating chatbot-like models. So GPT 3.5 is a basic model, which is a language model. But GPT 3.5 instruct model, typically the instruct is the word used in the model name. These are instruction-based models which are fine-tuned. So ChatGPT, when started, had 3.5 instruct model and deployment. So multiple things we can do in LLM development. RAG is another thing that we will discuss little later. LLMs are used in that application. So these are some of the information. We are moving close to this end of the session. GPT, Claude, many open source models are there. So GPT and Claude are proprietary, closed. These are open source models. Few approaches, mixture of experts, a lot of new developments have started coming, have came in off late. Long context meaning long windows, long sentences, multimodal meaning language also, images also, sound also, video also, everything together. Many advances have come in. This I'll not cover. Many limitations, hallucinations and other things. I'll just let you read very quickly. Many challenges, data is there, challenge is there, deployment, then of course, huge GPU need, ethical challenges, whatever your training data, it may have garbage also, it may not give right results, so many issues. All right, so this is what I wanted to cover. Emerging trends, you just go through it once. So these were large language models, but another set of models which are small language models. They're trained, their networks are small, maybe say 2 billion parameters, 5 billion parameters. They're small ones, but they have good linguistic capacity. Reasoning models, they are based on the recipe, how they arrived at an answer. These are those models, multimodal, as I just explained, agentic AI, continual learning, meaning runtime knowledge adaptation without full retraining. Many things are getting popular these days. That's about it. These are some of the papers which you may have a look. All right. That's about it, which I wanted to cover. By the way, this is my one pager, ChatGPT. If at all you can search for it. It's Sketchnote, which I think went viral. There's I think more than 1 million views across different platforms. You can have a look at it as well. All right. That's about it. There you go. Thank you.